Hey everyone, welcome back. We've just loaded the position data and computed its derivative using the function that we wrote ourselves, and we've plotted it here. Now, the next step we'd like to use for this data is to plot the peak of each oscillation versus time. We want to see how that decays over time. Let's see, I know I limited my time axis here to 10 seconds. Let's see what happens if we increase that to 40 seconds and take a look at the data, just to remind ourselves what that data looks like. That's a lot clearer. I can see that I have clear decay in the amplitude of that oscillation. So what we want to do is hone in on these peak points. And we need a structure to store those. So we want to talk about what the difference is between a list and an array. So let's make a list. I'll make a list called animals, and my list of animals will be aardvark, bear, let's say cheetah. Now if I say animals, I can see that there's my list. A thing I can do with a list is append it. So I could say animals.append donkey. That'll do, donkey. And now if we say animals, we get aardvark, bear, cheetah, donkey. So this is something that I can do with a list that I can't do with an array. A list is something called mutable. This means that when I create the list, it has a certain length, but I can change the length of that list. I can't do this with an array. Once I make an array, if I say animals equals array of animals, that is part of NumPy. If I say animals equals np.array, I have my animals now. If I try animals.append 5, I'm not able to do this. There's no attribute called append for animals. So if I want to keep track of what the peaks are, and I don't know how many peaks there will be in my data file, I need a list, not an array. I want something I can add one element at a time to and expand the amount of computer memory I'm using until I've recorded all of the peaks that I'm able to find. So let's get rid of animals, we don't need that, and we will create a new variable. So here we go, making our new variable. I'll call it peaks to record the indices of these peaks. Remember, if this X array has 1004 elements, the index is how many elements I count through to get to the element of interest. So peaks will be an empty list. I'm using square braces to initialize that list. Now, how could I diagnose a peak here? Well, if I look at a group of data points, I can see that a peak is the maximum of its local group of, let's say, 5. We could tweak that if we needed to. Let's say n equals, from the peak here I could go 2 in each direction. Let's say 2. So now we can say for I in range n comma len of x minus n. So we're not starting at the beginning of the array, we're starting 2 data points into the array and looking for a particular signature to find a peak. We're going up to n data points from the end of the array. Notice that when I hit return there, I'm already indented because I typed a colon. The notebook knows that I'm inside a loop. I'll say if x of I, the element I'm currently looking at, equals. Now in Python, double equals like this means a test of equality, whereas single equals, like here we said vx equals, single equals is an assignment. It says vx, the symbol called vx, is equal to whatever I put on the right-hand side. If I want to test whether something is equal, I need a double equal sign. So I'll say if x of I equals max, that's a built-in function in Python, of this sub-array of our whole array, I minus n, colon, I plus n, colon to enter this conditional statement if, I will say that peaks dot append, and what do I want to append to my list? I want to append the index of that maximum element. So let's shift enter, run this, and type peaks to see what we've recorded. And I see I have indices here. These are not the values of the peaks. They're not the values of the time when I have peaks. They're the values of the indices at each of these peak values. So let's see what that looks like. I can duplicate my plot here, where I'm plotting position versus time. So let's make a new figure. We'll say plt.figure. And remember, we've been saying fig size equals 25,8. That gives us an aspect ratio for our plot, and plt.plot x, t, x. And I would also like to plot plt.plot t of peaks. Remember, that's just the indices of the peaks. X of peaks. And let's make this green squares. And run that again. And we see these green squares have been installed at the peak of each oscillation here. So we've identified the peaks of each oscillation. And that's the first step we want to execute in identifying the rate of decay.